This lesson is on the Binomial Theorem, which gives you a way to multiply x plus y to the n for a number n. It's called binomial because bi means 2, and there are two terms, an x and a y. The formula for x plus y to the n is the sum from I equals 0 to n of n choose I, x to the n minus I, y to the I. We're going to prove the formula first before we do some examples. This proof is done by induction. So we're going to start with the base case, n equals 1. And when n equals 1, x plus y to the 1 is just x plus y, because any power to the 1 is itself. And we need to check that that's the same as the formula. So the sum, I equals 0 to 1, of 1 choose I, x to the I, y to the 1 minus I, which is 1 choose 0, x to the 1 minus 0, y to the 0, plus 1 choose 1, x to the 1 minus 1, y to the 1. So we're plugging in I equals 0 and I equals 1. 1 choose 0 is 1, y to the 0 is 1, 1 choose 1 is 1, and x to the 1 minus 1 is the same thing as x to the 0, which is 1. So we have an x and a y, and we just get x plus y, which is the same thing as x plus y to the first power. So the formula is true for n equals 1. We're going to check it also for n equals 2, just because these formulas sometimes are a little hard to get used to, so I want to work through one more example. And we'll go ahead and verify the case for n equals 2. So if we look at x plus y squared, we get x squared plus 2xy plus y squared, just multiplying in the usual way. So let's check that the formula gives us the same result. The formula says we sum from 0 to 2 of 2 choose I, x to the I, y to the 2 minus I. So that means 2 choose 0, x to the 2 minus 0, y to the 0, plus 2 choose 1, x to the 2 minus 1, y to the 1, plus 2 choose 2, x to the 2 minus 2, y to the 2. Now, 2 choose 0 and y to the 0 are both 1. 2 choose 1, remember that this is 2, and then we have an x to the 2 minus 1 is an x, and a y to the 1 is a y. And so I guess here we could say x to the 2 minus 0 is an x squared. 2 choose 2 is 1. X to the 2 minus 2 is x to the 0, that's 1. And then we still have a y squared. So we get x squared plus 2xy plus y squared, which is the same as just multiplying out x plus y squared. Now we're going to do the inductive step. So suppose the theorem is true for n equals k, and we want to show it is true for n equals k plus 1. X plus y to the k plus 1 can be factored as x plus y times x plus y to the k. And since we've assumed the theorem is true for x plus y to the k in our inductive hypothesis, we can rewrite that as the sum from I equals 0 to k of k choose I, x to the k minus I, y to the I. Now we're going to distribute the sum over x plus y. So we take this sum and multiply it times x, and then we multiply it times y. In case you're not following this step, it's basically just taking this large summation and just calling it c. And so we're going to multiply it times both, so it's like saying cx plus cy. I hope I can undo all that. Oh, I can't. But let's see, if we take that sum that's in the box and multiply it by x, that's just going to raise the power of x by 1. So instead of x minus x to the k minus I, we'll have x to the x to the k minus I plus 1. And when we multiply it by y, we raise the power of y by 1. So we'll have a y to the I plus 1. Then we want to shift the index in the second sum. So the second sum is going from 0 to k, and instead we want it to go from 1 to k plus 1. That way we can get back a y to the I. So if we shift all the numbers up in the sum, going from 0, instead of from 0 to k, but from 1 to k plus 1, then we need to shift all of the terms down by 1. So that way we're still summing the same numbers. We're not actually trying to change the value of the things we're summing. So if these go up by 1, then all the terms out here need to go down by 1. Therefore, the I becomes I minus 1. This negative I becomes negative I plus 1, because it's minus minus 1. and this I plus 1 goes down by 1, so it becomes I. Now we're going to pull the terms that each sum doesn't have in common out of the sum. So this one goes from 0 to k, and the other term goes from the other sum goes from 1 to k plus 1. So in particular, the second sum doesn't have a 0. We're going to pull out the 0, and that's k choose 0, x to the k plus 1, y to the 0, and we just get x to the k plus 1 if we plug in I equals 0. If we plug in I equals k plus 1 into the second sum, because the first sum doesn't have a k plus 1, we're going to get x to the 0, y to the k plus 1. And it's k choose k, because we have k plus 1 minus 1, which is just k. So that gives us this y to the k plus 1. So these two terms on the side have been pulled out. And then the sums have now a common range from 1 to k. So we have the sum I equals 1 to k of k choose I, x to the k minus I plus 1, y to the I, and then the sum I equals 1 to k choose I minus 1, x to the k minus I plus 1, y to the I. And notice that the x and y are the same powers, so we can combine this all into one sum and pull out that x and y. So this is x to the k minus I plus 1, y to the I, the sum from 1 to k, but we have two different combinations going on here. So we have k choose I plus k choose I minus 1. And that's the part we need to handle still. So can we make that a simpler expression? If we take k choose I plus k choose I minus 1, we have k factorial over I factorial times k minus I factorial plus k factorial over I minus 1 factorial, k minus I plus 1 factorial. We can get a common denominator by multiplying the left-hand term by k minus I plus 1, since this one goes all the way up to k minus I plus 1, and this one only stops at k minus I. And the right-hand side, this one only goes to I minus 1, but the left one goes to I, so we can multiply by I, and that will give us k minus I plus 1 k factorial over I factorial k minus I plus 1 factorial, plus I times k factorial over I factorial k minus I plus 1 factorial. The denominator is the same, so we just combine the fractions, and then we have k minus I plus 1 plus I all times k factorial, or in other words, the numerator becomes k plus 1 times k factorial, and you can absorb that into the, so this is 1 times 2 times 3 up to k times k plus 1, which is just k plus 1 factorial. Now, k plus 1 factorial over I factorial times k plus 1 minus I factorial is by definition k plus 1 choose I. So the sum of these two combinations is actually equal to this combination, and we can plug that in to our formula. So we get k choose I plus k choose I minus 1 is k plus 1 choose I. And this would be x to the k plus 1 plus the sum from 1 to k of k plus 1 choose I, x to the k plus 1 minus I, y to the I, plus y to the k plus 1. Now this is just the 0th term if we plug in 0 into this middle summation. And this would be the k plus first term if we plug in k plus 1 into the summation. So we can combine all this into one sum. The sum from I equals 0 to k plus 1 of k plus 1 choose I, x to the, well, it's k plus 1 minus I, y to the I, which is the formula. So if it's true for k, then it's also true for k plus 1, and therefore it's true for all values by induction. So let's actually use the binomial theorem now to expand a polynomial, which is the purpose of learning this. So we want to multiply 2x plus 3 to the 4th power. You could do this by hand, but by hand you'd have to do this in steps. So you'd first take 2x plus 3 squared. Well, I say by hand, I mean by the FOIL method or something. So distributing over and over again. You could square 2x plus 3, take that polynomial, multiply it again by 2x plus 3, get a cubic polynomial, multiply it again by 2x plus 3. But instead of doing all that, we can use the binomial theorem where this is x and this plus 3 is y. So you write the terms one at a time. Since we're going to the fourth power, we're going to have 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Then we're going to take the 2x and put a 2x to a decreasing power. So it's to the 4, to the 3, to the 2, to the 1, and to the 0. Then the 3 goes in an increasing power. So we have a 3 to the 0, to the 1, to the 2, to the 3, to the 4. And in the next line, we just multiply out everything except for the choices. So it's 4 choose 0, 16x to the 4, 4 choose 1, 24x cubed, 4 choose 2, 36x squared, 4 choose 3, 18x, 4 choose 4, 81. And that's just, for example, like this 81 comes from 2x to the 0 is 1, and 3 to the fourth power is 81. And this 18x would come from 2x to the first power is 2x, and 3 squared is 27. Oh, so this looks like a mistake. That should be 27 times 2. I think that should be 54, not 18. But yeah, you just multiply out the coefficients to get the numbers here. And then we want to multiply by this 4 choose 0, 4 choose 1, 4 choose 2, and so on. You might not remember what these are, but you could reference Pascal's triangle. So if you look at row 4, those numbers are 1, 4, 6, 4, 1. So we can plug them into this polynomial as 1, 4, 6, 4, 1. And this should be the answer, except as you saw above, I made an arithmetic mistake in my notes, but that's the answer of 2x plus 3 to the 4 if you get the computations correct. There's actually another kind of problem you can solve, which is related to probability. So let's say that there are 3 bags, and each bag has 2 red balls and 4 yellow balls. 1 ball is drawn from every bag. What I want to know is how many ways are there to get 3 red balls? How many ways are there to get 2 red balls and a yellow ball? How many ways are there to get a red ball and 2 yellow balls? And then how many ways are there to get 3 yellow balls? Okay, it sounds like a lot of work. So we've got 4 different problems, and we could try to do 4 individual computations. But instead, what's actually true is doing these kinds of choices is the same as multiplying polynomials. So we can use the binomial theorem. We have 2 red balls and 4 yellow balls in each bag, and there are 3 bags. So we could represent that with this polynomial. There are 2 red balls and 4 yellow balls in a bag, and then we raise that to the 3 because there are 3 bags. So this 3 up here in the exponent is the 3 bags. By the binomial theorem, we have 3 choose 0, 2r cubed, 4y to the 0, plus 3 choose 1, 2r squared, 4y to the 1, plus 3 choose 2, 2r to the 1, 4y squared, plus 3 choose 3, 2r to the 0, 4y cubed, as the expansion of this polynomial. Now plugging in the values, the 3 choose 0 is 1, 2r cubed is 8r, 2r quantity cubed is 8r cubed, 4y all to the 0 is 1, and 3 choose 1 is 3, 2r quantity squared is 4r squared, 4y to the 1 is 4y, and so on. So you can multiply this out and combine the coefficients, and this is the result that you get. And those numbers actually answer all the questions in one shot. So how many ways are there to get 3 red balls? Well, there's 8 ways to get r cubed, which would represent 3 red balls. There's 48 ways to get r squared y, which is like 2 reds and 1 yellow. So that means there's 48 ways to get 2 reds and 1 yellow. There are 96 ways to get 1 red and 2 yellows, so 96ry squared, which is 1 red, 2 yellows, and 64 ways to get 3 yellows, so 64 ways to get a y cubed.